on the test from this one. So what we did, okay, the other day we introduced the system. The cylindrical coordinate is going to be the polar coordinate in 3-dimensional. In the case of the polar coordinate, remember we changed the x into the r cosine of the data and the y into the r sine of the data, and the point would be r and data rather than x and y. But in this case, we have a 3-dimensional. In the 3-dimensional, we are going to keep the z to be constant. We fix the z. You see, this is what we talked about the other day. You see, the point that you have is x, y, z into the rectangular coordinate. So we change this x and the y to the r and the data, but we keep the z as is. So in 2-dimensional, you see, if you project it, means if you find the image of this 3-dimensional solid or put this point into the xy coordinate, your desk, your table, okay, if you do this one, you're going to get the polar coordinates. So when it's a polar coordinate, everything is going to be like the one that we did before. So your x would be r cosine of the data, y would be r sine of the data. And if you want to integrate, you integrate respect to the r first, then respect to the data. R is going to be the radius that you're going to use, okay? And the data is going around the circle, 0 and 2 pi, unless there is going to be any restriction. So when you want to integrate, we have to switch. So what I would like to do is we'd like to see how we're going to go from one side to the other side first. Then we introduce the integration. The integration is clear because we already know what's happened here. Remember, if you want to find this one, the double integral, we change it into the double integral, but your differential would be what? R d r d data.
I guess
So there's going to be a z extra. Okay, any question? So let's go from one side to the other side a little bit to get to know the feeling of what is going on with this system. Okay, so your job is going to be converting, okay, an equation would be given to you, then you have to convert it. But I'm going to give a couple of points to get to know this system, okay? So this example is going to be just to get the feeling how you change from one system to the other one. Then we change it to the integral, okay? So for example, suppose you have a point, you want to convert it. Suppose you want to convert this r data z, which is cylindrical coordinate. It's given to you, for example, this is going to be the 2 pi third, and the 5. That's in cylindrical coordinates. You want to move it to the rectangular coordinate, to rectangular. Okay, rectangular coordinates. So when you move it to the rectangular coordinates, your point would be what? Your points would be x, y, z. Okay, so this would be easy to do because the z would be the z. So z stays as 5. So you have, this is going to be your r, x, this is going to be your, this is going to be your r is equal to 2, and the data is pi third. So you write the formula for the x, y, z, and you get the result. Okay, so the solution is going to be, your reading from this part is going to be that you have that the r is equal to 2, data is equal to the 2 pi third. Okay, your z is equal to 5. This would be unchanged. So you have to find what? You have to find the x and the y. But we know the formula for the x in polar coordinate. X is r cosine of the data. Its substitute is going to be 2 cosine of the 2 pi third. 2 pi third under than 20, the cosine is negative 1/2. So it's going to be 2 times the negative 1/2. So that gives you a negative 1. So that would be x. Okay, you go with the y. So y would be r sine of the data. So it's going to be 2 sine of the 2 pi third. 2 pi third second coordinate. Okay, sine is positive and it's a radical 3 over 2. So it's going to be 2 times radical 3 over 2, which is going to be root 3. That's it. So the point in x, y, z coordinate would be presented by what? Your x is negative 1, Okay, this is -1, and your y is radical 3, and your z is 5, and then you're done. Okay, so it's a conversion of the representation of the point from the cylindrical coordinate into the xyz. Any question? Because the z is fixed and the leftover is polar coordinates. Okay, when we go to the, after your test, to the spherical coordinate, in that case, everything would be different, but not this one. Question? So let's do it the other way around. The other way around. If x, y, z is given to you, you want to change it to the, okay, r, theta, and z. So the next example is going to be this one. So you want to convert this time the other way around. Suppose you want to convert what? A point in xyz coordinate is given to you is like a -3√3, okay, and -3 and 5. So the point is in rectangular coordinates. Now you want to change it into the cylindrical one. So convert this one to, okay, to cylindrical. That's it, cylindrical coordinates. So the cylindrical coordinate form is going to be r, theta, and z. Okay, that's it. Again, your z is fixed, is 5. So you have to find the r and the theta. Solution. So start with the given information. Your information is what? Your x is -3√3. Your y is -3. And your z is 5. Again, z is fixed. Okay, z is fixed. So what you have to do is you have to find the r and you have to find the theta. Again, it's a polar coordinate. So you know that for the r, you go with the formula for the r, which is the square root of x squared plus y squared. Then you substitute. So that gives you negative radical 3, okay, all squared, and plus a -3 squared. Is going to be equal to, and that would be 9 times 3 would be 27. Okay, you get 27 plus 9 is a radical 36, which is equal to the 6. So this is your r. R is a radius, so it's going to be a positive number. Okay, now you've got to be careful when you want to find the data, is like you did before. We go with the tangent. Okay, the tangent of the data, you know the tangent of the data is y over x. The formula in polar coordinates. So your y is a -3. It's going to be -3, and your x is -3√3. You simplify that, give 1 over radical 3. Okay, you rationalize it. So that gives a radical 3 over 3. You have to pick the angle as we did for the polar coordinate. You have to check to see where your point is, in which quadrant are you in. Okay, because that would be important. So where is the point? Your point x is negative, y is negative. You see, negative, negative. So your point is here. Okay, so this is going to be the one. Okay, so this is the point. So the angle that you pick must be this one. Okay. Okay, so that's it. So the tangent, radical 3 over 3 is the tangent of the 30 degrees. It's the 30 degrees, but you have to bring the 30 degrees here. So this means you have a 30 degrees and 180, make it to the 210. So the data is going to be 7/6. So you have to pick the correct one, because you can have a 30 degrees or you can have 210. But you have to find the location of your angle and then identify location of your angle is here. Location of your point is here. So location of your point is here, so the angle must be, okay, 210. Any question? So the representation of the point in the, okay, in cylindrical coordinates, r, theta, and z. So your R is equal to the 6, your data is 7 by 6, and your Z is fixed, 5. And then you're done. Any question? But the one that you are going to be interested in is because you are going to have a function. You are going to have a function that would be given to you in XY coordinates. Then you have to convert it into the cylindrical form when you want to integrate. So we're going to work on a couple of equation to see what's going to be the conversion when you want to do the equation. And then we go
Professor,
to the integration. Yes.
hi, I'm sorry, I have a question. How did you get to 7 pi over 6?
You see, you check the data, where is the position of your point? You see the point X is negative radical 3 over 2 and the Y is negative 3.
Oh,
So your point is in the third quadrant.
okay,
Since the third, you pick the 7 by 6. If the point was in the first, you look for the 30 degrees.
okay.
Okay, so
Thank
that's the only point that you have to be concerned when you want to pick, it's in the polar coordinate or cylindrical one, and later on in the spherical one. Okay, any question? Now let's convert equations, which is more important when we want to integrate. And because in all the integrations, you have to convert the function to be able to integrate it. So I'm going to give you the famous one. You see, when you are in a polar coordinates, so you have R, data, and Z. So what we do usually, we solve for Z. You see, this is going to be a situation that you're going to have. So the example is, we want to find an equation of this form. Find an equation. Find an equation of the form. Equation of the form Z equal to f of R comma data. So your function would have x, y, z when it's given to you, okay? So you have to write it down in this form. If you write down this form, then you did convert it into the cylindrical coordinate, and then you'll be able to integrate it. So find an equation of this form for given surfaces. For given surfaces means it's going to be a function of 3 variables. Equation containing 3 variables. We know that. The graph of the equation containing 2 variables, which is going to be a 3-dimensional solid. We call it the surface. So I'm going to give them some famous one that we're going to use. Okay, this is very popular. X squared plus y squared plus z squared equal to the 9. What is the graph of this equation? X squared plus y squared plus z squared equal to 9. Anybody? It's going to be what? Yes, a sphere. I didn't, it's your guy. It's a sphere. It would be very popular case for the spherical coordinate. But sometimes this would be given to you in a, cylindrical coordinate. So you have to change it, you see. In a spherical, in the cylindrical coordinate, you want to write it down in this form of the R and the data. So this is the way you do it. Z is fixed, remember? Z is fixed, so we have to change the X and the Y. So the solution is going to be, you are going to substitute. You say, oh, okay. So what I have is this one. You substitute, your X is, you're going to substitute for X, R cosine of the data. You substitute for Y, it's going to be R sine of the data. But remember, the Z is Z. You're not going to change the Z because this is the cylindrical, okay? This is going to be cylindrical coordinate. Okay, so substitute. So if you substitute here, so that gives you R squared, you get R squared cosine squared of the data. Then you get the R squared sine squared of the data, and you keep the Z squared equal to the 9. Okay, now you know that you factor out the R squared. The leftover would be cosine squared plus sine squared, so that gives you all together, you are going to have the R squared. So this is going to be r squared plus z squared equal to the 9. You see? Any question? You solve for z and then you done.
Professor,
Yes.
if you factor out the r squared, wouldn't
Yes.
wait, never mind. Sorry, my bad.
Okay. Okay, then we solve for z. So that give you z squared equal to the 9 minus r squared. Okay, you take the square root, it would be positive negative 9 minus r squared. You see? So if you have a sphere, if you have the sphere, if you want to change it, convert the equation into cylindrical coordinate, this would be the version that you're going to have. So it's like, if you consider the upper sphere, hemisphere, if you like, hemisphere, the top and the bottom one. So one of them will represent the top, the other one will represent the bottom one. So if you get a chance there to convert the integral, in a minute we are going to do it. So if you get this type of situation, this is the way you're going to convert it. Any question? So this is the equation in, XYZ coordinate, and this is going to be the equation in cylindrical coordinates that we need. Any question? So this is one of them. The other one, again, this is very popular again. How about this? X plus Y plus Z equal to the 1. What is the graph of this one? Do you remember? X plus Z plus X plus Y plus Z equal to 1. Any idea?
Plane.
A plane, yes, very good. It's a plane. Yes, we move the one to the other side. It's a plane, very good. It's a plane, so you want to change it. Again, your Z would be, you fix the Z because the Z is permitted in the cylindrical coordinate. So you have to change the X and the Y again. Okay, so the solution is going to be, you change the X into the R cosine of the data. Okay, Y equal to the R sine of the data. Z is Z. You fix the Z. So in this type of problems, always your Z is going to be a function of R and data because you fix it here. Again, you substitute, and if you get a chance, we can simplify it. If you substitute, that gives us R cosine of the data, okay, plus R sine of the data, plus Z equal to 1. There is no chance for simplification. You just solve for Z. If you solve for Z, so that gives you 1 minus, okay, it's going to be 1 minus R cosine of the data minus R sine of the data. And you're done. You see, this is it. So Z is a function of, it's going to be a function of R and data. So it is possible, always it's possible. Always it's possible to write the Z as write a Z as a function of R and data. Any question?
Yes, I have a question, Professor.
Yes.
What section is this?
What section is it?
Yeah.
It's the one that we talked about the other day. It's a section 14.7.
Thank you.
Okay, 14.7 cylindrical coordinates. Okay, any question? Now we are ready. This is just the preliminaries. So we are ready to convert a triple integral in XYZ into what? Into the cylindrical coordinate. Cylindrical coordinate. So what are we going to do? Z is fixed. So the Z part is as before. The leftover, forget about Z. The leftover would be a double integral. A double integral in X and the Y. And we already talked about it, how we're going to convert a double integral into what? Into the polar form, remember? Because this is exactly what would happen over here. So the Z part stays the same. So if there is going to be any Z, of course, we have to write the Z in terms of the R and the data. So you can integrate safely respect to the Z first. When you integrate respect to the Z may be a fixed number, or it may be a function of R and the data. When you're done, the leftover is going to be just, you have the R and the data as you did it before. So integrate respect to the r, then it's the integrate respect to the data. And remember when we did the polar form, there was an extra r, Jacobian. So that would be the same over here. So the interpretation or the conversion, because you already done the big one, which is a two-dimensional. So, you are ready to change it quickly into this format. So there you are, triple integral, okay, triple integrals, that's it, triple integrals in cylindrical coordinate. So from now on, sometimes they give you instruction, or sometimes you see it yourself that it's easier to change it to the cylindrical coordinate, but we usually ask you to do it. Coordinates. That's it. So as we did it before, there's going to be a region that you have to integrate on it. That region can be a cube, can be a box, or can be type 1, type 2 in two-dimensional. So we change from x by z into the r data and z. So this is going to be the situation that you have for a given region. For a region, that would be the domain of integration. Region, we usually call it W of the form. This region must be a collection of points in cylindrical coordinate type, okay? So this is it, the W is equal to, it's going to be a collection of points, but your points are in this form, R, data, Z. So you are in cylindrical coordinate. Then you see this data is an angle, is usually between 0 and 2 pi, unless there is a restriction. So, we assume that this is going to be between data 1, data 2, as in polar coordinate. Then you have R a radius. So it's going to be between two fixed numbers. The axis, we call it alpha and beta. This is data R. Then you get the Z. This is Z as you saw it. Z can be a function of R and data. That's why you have to integrate respect to the Z first. So Z would be a function. I'm going to call it Z1. It may be a fixed number. Z1 of R and data less than equal to the Z less than equal to the Z2. But this can be a function of R and data. Okay? So we have a collection of points in this format. So the first one can be a function of R and data, but the other two are usually a fixed number. If this is going to be the case, now the triple integral from the XYZ coordinate to this new form is going to be, so the triple, okay, the triple integral, the triple integral that you want to find, see 1, 2, 3 over W. But your original function is the function of x, y, z, okay, and dv. That's a triple integral in a rectangular coordinate. Now this is going to be equal to what? Equal to this form in the cylindrical coordinate. We get triple 1, okay, but this is going from data to data 2. This means you integrate respect to the data at the end. Then this is going to be from alpha to beta. This means you integrate respect to the R in the second step. And this means Z1 to Z2. This means you integrate respect to the Z first. Okay, that's the limit of integration. Now, you keep the Z as is, but you change the X and the Y into the polar coordinates. So as we did, you have to convert this equation into the what? Into the cylindrical form. So to convert it as I did it, you change the X into the R cosine of the data, Y into the R sine of the data, but you keep the Z. Okay, you keep the Z, but remember there is an extra R because you do the polar coordinate as we did it before. So don't miss this R, otherwise your integral would be complicated. But you integrate respect to the Z first, then you integrate respect to the R, and at the end you integrate respect to the data. You see? If you just, if you forget about the Z, It is what? It is just a polar coordinates. So the projection of these three-dimensional solid into the two-dimensional is just a polar coordinate. That's why I'm going to explain it. Note that if you forget about the z, if you're going to be in two-dimensional, you can have a d as we did before. It's going to be a collection of points of the form of the r data. Okay, data is going to be between data 1 and data 2, and your r is going to be between alpha and beta. This is the projection. The shadow is the projection. Okay, the projection of your region of W onto, okay, on XY plane. Okay, this is going to be the one. So you can think about it as so you can, just give you a better understanding that if you want to find the triple integral of f of x, y, z dv over the region of W is like you keep the double integral as is on the region D, but you find the integral respect to the z first. It's f of x, y, z dz from z1 to z2. When you're done, you just integrate respect to the x and the y. So this simply means if you forget about the z, it's a double integral. It's a double integral that you would like to evaluate it into the polar form. So that's why everything you learn into the polar form would help you to be able to do it. So first you have to take care of the z. And the way you are going to set it up is going to be exactly the same. You just check to see what would happen to this r and the data in two-dimensional, because you have to find the limit of integration for the data and the limit of integration for the r. Then then easily can be done. Okay, so this is the generalization of the polar coordinate from the two-dimensional case into a three-dimensional that we are going to have. Any question? So let's do it. We give you the instruction. We ask you to use cylindrical coordinate to do these type of problems. These problems are complicated. If you don't want to use the cylindrical coordinate, some of them are impossible to do. Okay, so they are very typical problem. They cannot make it complicated, because it must be of the type of these cylindrical one, and it must be in the way that if you forget about the z, the leftover is going to be polar coordinate. So it's usually a straightforward integral, really. We don't have any difficulty. There are a couple of tricky ones. I'm going to do all of them. So on Thursday, when Professor Scott is coming and just help you with the review, that we already give you the solutions. So I'll do the cylindrical coordinate myself. There are 2 problems on that one, so that you'll be ready for it. Okay, so let's do it. Any question? So this is your job. Take care of the z first. The leftover is going to be polar coordinate. If your integral is complicated, you probably missed the r here. You see this extra r is due to what? Due to the polar coordinate that you use it. We call it Jacobian. After your test, you will see, we do all of them together, and you will find out why. Anytime you change the variable, you have to pay for it if you like. So that's it. That's the r that you have. Okay, so give you example how we're going to operate with this cylindrical coordinate. There are 2 groups of problem, and I give example from both 2, and then you'll be fine. For this 2 on this quiz in this test, and 2 on the final. Okay, there you are. This is type 1, straightforward. Apply cylindrical coordinate to integrate. Apply.
What did I bestow my eyes upon?
Okay, you will mute yourself.
Like a sucking sound.
Okay, mute yourself. Okay, that's one. So apply cylindrical coordinate. Cylindrical Okay, apply cylindrical coordinates. To evaluate the integral. To evaluate. That's it. What is the integral? 0 to 1. Negative 1 to 1. And negative 1 minus y squared to the square root of 1 minus y squared. And the function is x squared plus y squared, everything to the half. Okay, then the dx, the dy, the dc. You see, this is the integral. This integral in xy coordinates. So you have to change it to the cylindrical coordinates. Okay, you change it to the cylindrical coordinate and then you integrate it. So this is the way you do it. You have to change this region that you see. Okay, you see x, they give it x first. So x is between these two. Then you do the y is between negative 1 and 1, and your z is between 0 and 1. So you identify this region first, okay? And then you switch it into the polar coordinate, and then you do the job. This is the way you do it. Solution. So introduce this region to yourself. Just read these numbers that you have. Okay, as I talk about it, this is x. So we say that and note that what I have in rectangular coordinate. I have the x is between, x is greater than or equal to the negative radical 1 minus y squared. Okay, less than or equal to the 1 minus y squared. That is x. Then I do the y. So my y is between negative 1 and 1. Okay, then I have the z. Z is between, okay, the z is between 0 and 1. Since you are in a, okay, cylindrical coordinate, your z is fixed. So this would be unchanged. Okay, because the z would stay the z into the cylindrical coordinate. So that would drop you into two-dimensional. So you have to identify what type of region is this one, because you have to change it to the polar coordinates. Okay, so what you do is this is it. You start with the x. So you let them to be equal to each other. So you have the x is equal to the positive negative 1 minus y squared. In order to find out what shape is this one, square it. So that give x squared is equal to the 1 minus y squared. So that give x squared plus y squared equal to 1. What shape is this one? X squared plus y squared equal to 1. X squared plus y squared to 1. What's the graph of this equation?
Circle.
A circle. Very good. A circle. A circle is centered at 0. The radius of 1. 1, 1, 1, 1. Okay, this is going to be your circle. Okay, if you graph it, that is going to be your circle. Okay, that's a negative 1, and this is 1, and the bottom one, negative 1, and the top negative 1. Now you check to see if you have full circle or half circle. You see your x is between these two. These are going to be semicircle. Semicircle. So with this x, you need all of them. Okay. Then you check the y to make sure your y is between negative 1 and 1, 2. So it's going to be top, bottom. So this means your region is going to be all the points in this circle. Any question? So it depends. If this is going to be between 0 and 1, you may get a quarter of a circle, like the one that we did it in polar coordinates. Okay, so it depends on the shape of this graph and the region that you are going to have. Okay, now you change this one into the polar coordinates. Okay, you change to the polar coordinate. R would be the radius. Okay, so R is the radius, so the radius is 1. So R is going to be between 0 and 1.
Professor, could you explain? So we see that y is between -1 and 1.
Yes.
But how do you know what x is between?
X is between the semicircle, the top and the bottom.
And you know that's a semicircle just because you know that when you solve for it, it becomes a circle, and
Yeah,
then
yeah. You
Okay.
know that this square root is the top because it's positive. This negative one is the bottom. That's why I write positive negative root 1 minus y squared. Okay,
okay, thank you.
so that would be very crucial to see. I'll give you another one in a minute. Sometimes you may have only the top. So in order to get the top, this would represent the top, that number, you will see it. But in this case, we have no doubt about it. That's going to be full circle. Okay, any question? So your R is always the radius between 0 and 1. The data is going to be, since you consider in full circle, so you go around the circle, so the data is going to be between 0 and 2 pi. Any question? And your Z is already determined. So the Z is between 0 and 1. Okay, because in order to convert it to the cylindrical coordinate, you need these three altogether. Any question? Now we are ready to check the
Professor,
change. Yes,
can you go over the part of how you got the theta?
you see the data. So your region is a circle.
Uh-huh.
So the data is going to be, if you go around the circle, if you go
Oh,
around
okay.
the unit circle,
Okay.
you get 0 to 2 pi.
Oh,
If it's
okay.
going only the top, it's going to be 0 to pi. If it's going to be just a quarter, it would be 0 to pi half.
Okay, got it. Thank you.
Okay, okay. Now we are ready to convert the integral. Okay, this is the way we're going to do it. So I'm going to, you may call the integral I, so we are not going to repeat it anymore. So I, the integral, is going to be equal to, remember we talked about it. We change it to the integral respect to the data at the end, so it's going to be 0 and 2 pi. Then in the middle, we integrate respect to the R, so the R is between 0 and 1. And at the beginning, we integrate respect to the Z, and the Z is between 0 and 1. You see, look at this. That's exactly how you change it. That was the X, Y, Z that we change. Okay, when we change it to the cylindrical coordinate, it's going to be Z, R data, Z, R data. So the Z is fixed between 0 and 1. So the R is between 0 and 1 because of the radius, and the data is between 0 and 2 pi. Now the function. You have to change your function. The function is x squared plus y squared, and we already talked about it. X squared plus y squared is R squared, because x is R cosine of the data and y is R sine of the data. You have to substitute usually to get it. Okay, you have to substitute to get that one. Okay, that's it. But x squared plus y squared, we know it's going to be R squared. Yes, z is fixed in cylindrical coordinates. Z is z. So you change the other one into the R and data. Okay, so that is going to be the case. Yes, you have to integrate respect to the z first, because z can be a function of R and data only. So you have to take care of the z first. Okay, now we change the function. This is going to be R squared because it's easy. Otherwise, you substitute. So it's going to be R squared. Okay, R squared to the 1/2. Now, the integration, remember there is an extra R. R dz, because we integrate respect to the z first. dr d data. Okay, this is our
In the first version, we integrated with respect, it went dx, dy, dz. So are we going backwards now?
No, we didn't. No, because you see the structure of your cylindrical coordinate of this form. It's exactly the same. It's exactly the same because in this case, you see in the XYZ, you can switch this as many times as you like. But the shape of the function, the shape of the limit of integration that's given to you, it suits into the dx d by dz. Okay? So your cylindrical coordinate is fixed. It's a z. Okay, this one, nothing to do with this. Okay, this is the one that you decided yourself to get these numbers, because that's that order suits the rectangular coordinate. But in the case of the cylindrical coordinate, as we arrange it, we arrange it to Z first. You see, your variable is going to be what? R data Z. So you are going to be concerned with the DZ, DRD data. Because of the shape of the problem that you have, your Z is fixed, it's between 0, 1. So that's why we are going to have a case that your Z is not going to be a fixed number. Then you may have to change it. But this is exactly as is. Any question? The region would determine how you're going to integrate here. Okay, when you change the region from the XYZ coordinate into the polar form. Question?
I just wonder, well,
Yeah.
we didn't do anything to the Y. Do we just leave it? We just changed the
We
the-
did to the Y. Why we didn't do anything to the Y? Y is part of the X and the Y here. You see, since Y is between -1 and 1, we realize that we're using the full circle. You see?
I
So
see.
how you see, how do you know that you have to use the full circle, not the semicircle, quarter of a circle, you know? So all of them would help you to find out what part of the region are going to use. Okay, otherwise you can't do it. If they give you something like 0, 1 here, then it's not going to be consistent. 0, 1, you will see it. If it's going to be 0, 1, if you're supposed to do it for the half circle, then it cannot be between -1 and 1. Okay, so all of them together, you put them all of them together to find out that it is the, you see, this is going to be the one, because that would have effect on the way you are going to pick the data. You see, since it's a full circle, the data is going to be 0 to pi. Why? Because we know it's a full circle. Okay, any question? So that's very important to pay attention to the version that you're going to give in. You may be given 0 to the radical 1 minus y squared. If that was the case, quickly that is going to be what? That's going to be semicircle. Okay? Like the polar coordinate that you have. You see that version of the xy is going to be just the polar coordinate. Any question? Integral is very easy, of course, to find. Most of the time this is the case. R squared to the 1/2 is the radical r. So this would be what? This would be r. Okay, this would be r. So we have the r times r, which is r squared. So this is going to be, you get the 0 to 2 pi. Okay, 0 to 1. 0 to 2 pi, 0 to 1, and this is going to be 0 to 1. So we get r squared dz dr d data. So we integrate respect to the z first. Okay, integrating respect to z, integral of, what's integral of r squared respect to the z?
R squared Z.
That's it, excellent. Yes, r squared z. But z is going from 0 to 1. And when we're done, we come back and we go with the r and the data. Okay, so that's the case. Now if you put z equal to 1, that gives r squared. Z equal to the 0 would be nothing. So it's going to be 0 to 2 pi. Okay, 0 to 2 pi, 0 to 1. So that will give us r squared only. Okay, but it's going to be r. I write it down so that you know that r squared minus 0. Then the TRD data. So this is simply 0 to 2 pi, 0 to 1. Okay, we have only r squared, DRD data. Now we integrate respect to the r squared. It's going to be just r cubed. So 0 to 2 pi, that would give us r cubed over r over 3. Then r going from 0 to 1, d data. If you put if you substitute r equal to 1, that gives just 1/3. Okay, so it's going to be integral from 0 to 2 pi. You have 1/3. 1/3 d data is going to be 1/3 of the data between 0 and 2 pi. If you put the 2 pi, that gives you 2 pi third. So 2 pi third is going to be the final. I is equal to the 2 pi third. And you're done. You see, setting up the problem is the important part. That you get, this type of ideas. And they are going to be, they must be, nice region, nice symmetry, symmetrical, if you like, region to be able to take care of it. This type of problems. Okay, any question? So we give you a couple of them, you know, just to do it, then you get it, what's going on for these type of problems. And then that tricky one, that it's a number 10, I think, on the review. That's a famous problem. It can be done using a spherical coordinate or cylindrical. In both cases, it's interesting problem. I'm going to do that one myself. Okay, let's have another one quickly to get used to how you set up this one. So this one is very similar to the first one. Then I give you the third one, which is a little bit different than the fourth one, which is quite different. Okay, there you are. So the second example, so that was the first one for the cylindrical. Let's call this one number 1. Okay, again, cylindrical coordinate for this part. What is the integral? Again, it's very popular integral, -1 to 1. Okay, let's say I'm going to change it a little bit for this one. Let's have a -2 to -2 to 2. Negative, I don't want to go with the 1 to 1 all the time. So this is going to be, again, I have a -4 minus x squared. And this is 4 minus x squared. I changed the problem a little bit. So that would give me, what is this? You see, this one is I changed this one. It's going to be 0 to the, and that's a 4 minus x squared minus y squared. Okay. Your z is different. The other one that I give you, that was 0 to 1. So, and the function is dz, dy, dx. You see, this is an integral in, again, xyz coordinate. So we want to change it to the cylindrical coordinate to do it. Okay, again, if you want to do it, it's going to be very, very messy if you want to do it as is, and sometimes it's not possible. So again, you have to find the region. Just read the information that you have. Okay, you have the order is z, y, x. So x is right at the end. So your x is this time is going to be between negative. You set up this region and change it. So what you have, note that. Again, x is the last one. So your x is between -2 and 2. This is your x. The middle one is y this time. So your y is between 4 minus x squared and the 4 minus x squared here, the positive and the negative. And you have the z as well. So your z is between, okay, this is going to be your z. 4 minus x squared minus y squared. You see, the situation is a little bit different for this one. You can take care of the z later. Okay, keep this one as is, or you can keep it. Just do it now. So this is the 2-dimensional one. This is where you get the polar coordinates. So take care of this one first. Okay. Again, x is between -2 and 2. This time y is. So what is this? So you need to be equal. Equality again. So if you square it, so that gives 4 minus x squared. Again, if we move it to the other side, what's going to be the result? Is going to be x squared plus y squared equal to 4. What is this one?
Circle with radius 2.
Radius 2. Very good. So the radius is different. Okay. So we just get the graph of the circle at the radius 2. So that's it. So you have the 1, 2, 1, 2. Okay, and it's going to be 1, 2 up and down. 1, 2, 1, 2. So you are going to have a circle again. Okay. Then you check to see if you have the full circle. You see y is positive, negative. So the positive is semicircle on the top. Negative is done. And you have a -2 and 2. So this means, again, you are using the full circle. Okay. But the full circle, your circle, the radius is 2 this time. So your r is between 0 and 2. And since using the full circle, your data is going to be between 0 and 2 pi. This is it. Any question? Now, your extra job is here. How about Z? You see, Z is not a fixed number.
It's is it a sphere? If you square it, it'll be x squared plus y squared
No,
plus
no,
z squared
no,
equals 4.
No. We are not going to do this type of things for the squares. If you go to the cylindrical coordinate, if you go to the spherical coordinate in future, we do it, but not for the cylindrical. What a Z should be in cylindrical coordinate, you see? A Z should be a function of R and data, remember? Because you integrate respect to the Z first. So what you have to do if there is not going to be a number here, you have to switch it exactly as you did it over here. You have to change the Z into the function of R and data, you see? It's exactly as I did over here. Your Z is equal to what? The 0 is not important, okay? So you let the X to be equal to the 4 minus X squared minus Y squared. If you square it, yes. If you square it to move it to the other side, that give you what? That give you a sphere. But you are going to be concerning to the fact that the changing to the Z into the function of R and data. And the way we do it, you know that. This is going to be 4. You pull out the negative sign, so that gives X squared plus Y squared. You know that X squared plus Y squared is R squared. So this would give you the Z in terms of a function of R and data. So it's going to be 4 minus R squared. Because you integrate respect to the Z first, then respect to the R, respect to the R. So now you can claim that your Z is between 0 and 4 minus R squared. You see, this is a kind of a type 2 that you have. In the previous problem that I did for you, Z was between 0 and 1. So that's why we didn't care. But in this case, Z is a function of X and Y. Since Z can be a function of R and data, you have to switch it. If you are going to be in a spherical coordinate, that would be the other story for this type of problems. Okay, now we are ready to integrate it. We integrate with this information that the R is between 0 and 2, data is between 0 and 2 pi, and Z is between 0 and radical 4 minus R squared, which is valid argument. Valid argument because Z can be what? Z can be a function of R and data because it's a triple integral. Okay, now we set up the integral. Any question?
Yeah, how do you know which way to set the integral up?
I know very well. So
How do we know?
what's the formula? You see what we have? What's the formula? The formula is fixed. Okay, what was the formula? The formula is what? I equal to. Remember, we integrate respect to the Z first, then R, then data. So the last thing that you do is data. What is the limit for the data? 0 to pi. So that's a 0 to pi. In the middle, integral respect to the R all the time. What is the limit for the R? 0 and 2. At the beginning, you integrate respect to the Z. It's a fixed operation. Okay, integrate respect to the Z. What is Z? Z is between 0 and a radical 4 minus Y R squared. That's why you are okay if your Z is going to be between these two numbers, because there are a leftover of the integral respect to the R, respect to the data. Function. There is no function. The function is 1. The function is 1. Okay, so it's going to be 1. But the formula, remember? So the function is 1. I write 1 just for your information. But the formula was with what? Remember, extra R, integrating respect to the Z, integrating respect to the R, data. This is it. You see, the formula is fixed. The formula is fixed. When you change it to the cylindrical coordinate, this is the order all the time. Data, if you start from the left, data, R, Z. Any question? So the things that it's different from this problem is this part. Okay, that your z can be, if your z is not a fixed number, you have to write it down in terms of the r and data. How are we going to do it? You substitute. You see, x is r cosine of the data, y is r sine of the data. Since you have x squared plus y squared, x squared plus y squared is r squared. Okay, and then you'll be able to do it. Okay, integral is easy. Integrate respect to the z first, so that give you only zr. So it's going to be 0 to 2 pi. Okay, 0 to 2 because of the radius. Now this would be rz, integral rz. But remember, your z is between what? Z is between 0 and a square root of 4 minus r squared. And then when you're done, you get the dr and the d data. Okay, so it's going to be 0 to 2 pi, 0 to 2 pi, 0 to 2, substitute. C equal to the square root of 4 minus r squared first. So this is going to be what? Is r, a square root of 4 minus r squared. Minus what? Minus 0, because the z is 0. When you're done, you integrate respect to the r, then data. So when you have 0 to 2 pi, 0 to 2, okay, r times, since I want to integrate respect to the r, so I change it into the 4 minus r squared to the half, then the dr and the d data. Any question? Now you are going to integrate it. How are we going to integrate
So-
this one? Yes, question.
Oh, so all the like the intervals, like the x, y, and then the z are given to us, or like sorry, the dr, d theta in are given to us to solve this.
What do you mean are given to us? It's part of the formula.
Yeah. Sorry, yeah, that's what I mean.
Yeah, this is the formula. You see, whatever it is, when you design it, you have to design it in this format. Exactly this is the one you see. You're not going to switch. That x, y, z can be changed, but not this one.
All right, cool. Thank you.
Okay, it's because we designed it according to the, because that x, y, z, when it change, your region would be different. But at the end of the day, you have to identify the region in terms of the polar coordinates to be able to write this your new integral. Okay. Any question? So if you have any doubt about it, just let me know, because that's it. It's a very popular case. And then when we get to the spherical one, that gives us an idea. Okay, this integral, you know that this is going to be a particular, use a usual integral. You have to use U substitution. So this is going to be U. Okay, so what's going to be du or U prime? U is
Negative 2r.
negative 2r, and missing one is a negative 1/2. So what I'm going to do is I'm going to divide by negative 2 outside, 0 to 2 pi, and this is going to be 0 to 2. Then I multiply this one by negative 2r. So it's going to be kind of 4 minus r squared, okay, to the half, and this is going to be negative 2r dr, d data. This is, you know, the quick U substitution. So this is U, and this is du. So you integrated what? U to the 1/2 du, which is U to the 3/2 over the 3/2. Any question? So
Yeah.
you can do your substitution, but at this level, just do it. Yes.
Can you explain how, like, because I've seen this in the lecture as well, and I get confused about it. How come you have a negative 1/2 on the outside? Is it because you have a negative?
Because I need
2
a
and
negative
then-
2 inside, you see.
Oh, okay.
So always a number is missing, because if the R is missing, you can't do it. So that missing number, you can create it yourself. So I need a negative 2, okay? So I divide by negative 2 and multiply by negative 2 here.
All right, understand.
So
Thank
that
you.
will help, you know, that will help. We can do it quickly here. Because, okay, so you keep, yes, you get the negative 1/2 as is, 0 to 2 pi. Now you know that your substitution that give you to the 3/2, which is going to be 4 minus r squared to the 3/2, carefully, over the 3/2. and R going from 0 to 2. And when we're done, we come back and we integrate respect to the data. You have to simplify it. You flip the 3/2 into the 2/3. Okay, then you substitute -1/2. Integral from 0 to 2 pi. So that gives you 2/3. Okay, 2/3 times 4 minus R squared to the 3/2 from 0 to 2, then the t data. Okay, you can simplify these two. And you can pull out the 1/3 outside if you like. So that gives you -1/3. Integral from 0 to 2 pi. Make it easier, to handle the rest. They are all optional. Then you substitute R equal to 2. If you put the R equal to 2, so that gives you 4 minus 4 to the 3/2. Minus, you put R equal to 0, so that gives you 4 minus 0 to the 3/2. Then the t data. Okay, 4 minus 4, make it 0. And over here, we get a 4, so there's going to be -1/3, 0 to 2 pi. Okay, and this is going to be -4 to the 3/2. You know that 4 to the 1/2 would be 2, 2 cubed would be 8. You see, 4 to the 1/2 would be 2, 2 cubed would be 8. So this is going to be -1/3, integral from 0 to 2 pi, and that would be -8 d data. You put out the 8, so that gives you 8/3, 0 to 2 pi, d data. D data would be just data, and from 0 to 2 pi. If you put the 0, you get nothing. If you put the 2 pi, so that gives you 16 pi/3, the final answer. Okay, any question? So this is a very popular case. You better, check it for yourself. So they change it a little bit, but otherwise it's very popular because they want to know how you handle this part. Okay, how you handle the Z part that you have, because most of the time you have a fixed number for the Z, but this one is different. Okay, and then we can take care of it. Take care of the Z for this problem too. Okay, any question? So these are a kind of a straightforward one for this type of problems. So I'm going to give another one to make sure you understand this last part that we did. This type of problems can be done, as I told you, with the spherical coordinate as well, but the cylindrical is much easier. You will see it when we get to the spherical one. It's a little bit complicated, but it can be done. Any question?
I have a quick question, Professor.
Yes.
Yes. So on the second step, we have a R in front of the U.
Yes.
Where does the R go after that step?
You see, I did the U substitution. So I need the U is 4 minus R squared. So I need the du. What is going to be du? If you see this is U equal to the 4 minus R squared. So what's going to be the du? Du would be -2R dr. So this is U, this is going to be du. And when you integrate U, du would be, okay, U to the 1/2 du. That gives you this one.
Okay, thank you.
That R would be embedded in du, if you like, when you do when you do the U substitution. Okay, you can pull this one out and do the U substitution, do all the operation, then go back. Okay, but it's kind of, we do it right away. So this is it, -2R dr is your du here to get these numbers. Any question? Now pay attention to the next one. Again, you learn through the experience this format, especially the constructing that region. Let's see what is special about this one. It's very popular. It can be done with a spherical coordinate, but it's a very complicated problem. You have it when we get to the spherical one. So sometimes they force you to say, apply the spherical coordinate, but the cylindrical one is the one that's going to be interesting. Let's see what is special about this one. It's very similar to the what you did, but you'll be surprised about that part of the integration. It's very similar. Okay, so let's see. We want to find this integral, -1 to 1. Okay, and this is negative 1 minus x squared. I think it's one of those problem in your practice one, maybe. And I will post a extra point number 3 for you. You know that that's 5 points. And it's going to be very mostly, it's a short, it's mostly integration. So I that one. I have to change a little bit, a couple of problems because we haven't done the section 14.8, but I posted for you. Let's see what is special about this one. dz, dy, dx. It's very, very close to the what I did, or we did. Again, you see, you cannot randomly, give you some integration. It must be nicely designed because you must make sure that they are going to be connected, and when you get it two-dimensional, you get that format of the polar coordinate. Again, identify the region that you have. You see, it's an XYZ. Then convert it to the polar coordinate and get the R and the data. Okay, are you ready? Read the information. So I'm going to read the information. What do you have? The integral respect to the z first, the y in the middle, x at the end. So your x is between -1 and 1. Nice. The middle one is y, -1 minus x squared. You see, semicircle, the top and the bottom again. So that's your y. Your z is between what? Your z is greater than or equal to the square root of x squared plus y squared, and this time less than 1. That's your z. Again, you focus on the x and the y because you are going to be interested. You are not going to worry about this one much. Okay, as usual, this is up and down for the semicircle. So this is what you have. And this is how we're going to do it on the test. So it's going to be y squared, 1 minus x squared. So that gives you x squared plus y squared. You know that this is it's a circle. Okay, so this is going to be a circle. Unit circle. So we get the 0, 1, 1, 1, 1. Okay, so this is it from -1 to 1. You have a positive negative over here. So we have up and down. So we have the full circle. And you have a -1 to 1. -1 to 1, full circle. So the y is up and down. You see up and down. And the x is to the right, to the left. So that gives you nicely the fact that you are going to use the full circle. Any question? So R is clear. The radius is 1. So R is between 0 and 1. And the data is between 0 and 2 pi. So this is it. Any question? Now you have to take care of the z. You go back to see what you have for the z. You see z? Z is less than 1, but it's greater than radical x squared plus y squared. So you change this one into the R and the data. How are we going to change it? You see, z equal to a square root of x squared plus y squared. You know that x squared plus y squared is R squared. Because you have to change the z into the function of R and data. So this simply would be radical R squared, which is equal to the R. So your z would be between R and 1. That's it. So you identify the limit of integration for R data and Z. Any question? You see that projection into two-dimensional is always like a circle, semicircle, because it must be polar. It must be polar coordinate. It cannot be anything else. And the Z part, this is the Z part. If it's going to be a fixed number like the first one that we did, nothing to worry about between 0 and 1. But if it's not, whatever you have for the X and the Y, you substitute. X is R cosine of the data, Y is R sine of the data. But X squared plus y squared would be r squared. Okay, any question? Now you set up the integral. There you are. Remember, the formula is fixed for the integration. So the formula I equal to triple integral, and we know that we go with the data first. The data is between 0 and 2 pi. In the middle, we go with the r, 0, 1. At the beginning, we go with the z. Z is between what? Between r and 1. The function, change the function, but the function is 1. So nothing to do, 1. But you know that the formula is what? The formula is extra r, dz, dr, d data. A standard formula for the cylindrical coordinate. That's it. Any question? Very easy integral to find. You integrate respect to the z first, so it's going to be 0 to 2 pi. Okay, 0 to 1. Integral of r would be rz. Rz. Z goes from r to 1. Then we are going to find the drd data. Replace the z by 1. Okay, it's going to be 0 to 2 pi. Okay, 0 to 1. If we replace z by 1, that give you r minus. Okay, it's going to be minus. You replace it by r. It's r times r. I write it down so you know what's going on. Okay, and this is going to be drd data. So I replace the z by 1, and then I replace it by r. So that give you r times r would be r squared. So it's going to be 0 to 2 pi. Okay, 0 to 1. And we have a r minus r squared. Dr d data. Integrate, easy integral to find. So it's going to be 0 to 2 pi. Okay, integral respect to the r. So the first one would be r squared over 2. The second one would be r cubed over 3. Okay, evaluated from r equal to 0 to 1, and then d data. If you substitute 1, 0 to 2 pi, if you put the 1, that give you 1/2 minus 1/3. 1/2 minus 1/3. And if you put the r equal to 0, that gives you 0. Okay, it's going to be minus 0. Then the t data. Okay, so we get a 1/2 minus 1/2 minus 1/3. That gives you 1/6. Okay, 1/6 t data. So it's going to be 1/6 data from 0 to 2 pi. It's going to be 2 pi 6, which is the backtest, the final answer. Okay, so they are nicely, nicely can be done to get these numbers around. Any question? So they were all nice so far to get this number. Okay, so let me just give you another one. Then I give you a break. This last one is the one, okay, which is different from whatever you did so far. Okay, and this is where most of the people, they will make a mistake on this one. I think this is one of the problem in your, okay, I'm just checking it. This must be the problem number 10. Okay, but, or maybe similar, let's check. I do both of them for you if it's different. It's, yeah, it's very similar. I just changed the numbers. So this is going to be, oh no, it's a little bit different. The region is the same, but the integral is different. Okay, so it would be nice to know it. And this is a very, again, a popular problem in calculus 3. They usually, when they want to make it difficult for you, they ask you to use this spherical coordinate, but cylindrical one is the one. Okay, so what I'm going to do is I'll give you this one like a volume problem. You know that the volume problem, it can be done with the triple integral or just okay, or the double integral. So what we would like to do is we are going to ask you to do cylindrical coordinate. Okay, so just wanted to see if the way we are going to set up the problem. You may set it up for the volume problem. So use the cylindrical coordinate. This is the kind of second problem that we're going to see on your test and on the final. One of them just writing it, the integral is already given to you. The other one is you just set up the integral yourself. Use the cylindrical coordinates. Okay, cylindrical coordinates to find the volume. To find the volume. Okay, find the volume of what? Of the solid. Of the solid. Let's say solid G, if you like. Bonded above. Okay, bonded above by the sphere. By the sphere. The sphere is x squared plus y squared plus z squared. Okay, z squared equal to the 16. That's a sphere on the top, and below by a coin. It's like an ice cream. And below, okay, by the cone. Z
Hey,
equal
Professor,
to, yes.
are we gonna get a break at some point during class?
Yes, we can have a break. So we come back and we do this one. Okay, it takes time. Okay, that's a let's have something like a 10 minutes, 15 minutes. We come back and I do this one for you. And two problems on your review, which is related to the cylindrical coordinate. I'll try to explain myself. Okay, so coming back in 10, at most 15 minutes. Yes, then we continue. Okay, see you at 5.
And Professor,
Yes.
will you be giving over the topics that are going to be on the test since you're not going to be here on Thursday?
Yes, I give it the topics. Yes.
Okay.
Okay, see you soon. And I continue.
Yeah. Professor.
Yes, what's question?
I have a question. I was doing problem number 4 on the practice test.
What's the problem?
Problem number 4, it's evaluating the triple integral when it's a tetrahedron.
I've already given you the solution. Tetrahedron is very easy. What do you want? What's the
Yeah.
difficulty?
I was looking at you switch the coordinates. I think I kind of understand now why.
You see, you know that you have to have the limit of integrations. So your z is equal to the 6 minus 2x minus 3y. Okay. So your z is between these two numbers. When you let the z equal to the 0, so the image in 2-dimensional would be a straight line. 2x plus 3y to the 6.
Yeah.
Okay, that's a 1. Then you have to draw this line, x and y coordinates, intercepts.
Oh yeah, I got that.
Okay, so
My question is, you're evaluating it when you're fixing x to 0, but then you switch and you evaluate it from y to 0 as well on the second part.
no,
Is that what
I
you're doing?
didn't. No, I didn't. You
Okay.
see, I don't have the solution, but this is, you see, this is the usual practice. You see, you have the 2x plus 3y. This is the one.
Yeah.
Plus z equal to the 6. Okay. So your z is going to be 6 minus 2x minus 3y. So z is going to be this one. Okay. So you have to drop it down. You see z equal to the 0. You drop it into the 2x plus 3y equal to the 6. Now you are in 2-dimensional. Okay, to get 2-dimensional, you have to draw this line. Use the intercepts. If you let y equal to the 0, x would be 3. 1, 2, 3. If you put x equal to the 0, that give you 2. Okay, so this is going to be the region of region in two-dimensional, okay? And this is 0 and this is 3. So you have to decide how we're going to take care of this region. Is going to be a type 1 because you pick the x between 0 and 3, okay? Then you go up and down, you see, up, down, up, down, up, down. So the down would be 0, up, you have to find it. So you solve this one for y.
I got 2y minus
3y
two
equal
thirds
to
of x.
the, what's it, negative 2x minus plus 6. So y would be negative 2/3 x. Okay, plus 2. Okay. So your integral is going to be, that's it, the volume is going to be, you have this, okay, we go with the double integral in that case. I think that's one. Okay. You can go with the triple even at this point. But if you want to go with the double integral, I don't remember which one I did, but it's going to be the same thing. If you want to go with the triple integral, it's going to be 0 to z, 6 minus 2x minus 3y. Okay, then the number is 1 here. Okay, 1. Then your y is going to be between 0 and negative 2/3 of x plus 2. And at the end, your x is going to be between 0 and 3. This is the, and this is going to be what? This is going to be dc and dy dx. This is one way to do it. The other way to do it, you can do the double integral. If you do the double, it's going to be 0 to 3, 0 to negative 2/3 x plus 2, and you have to bring the function here. 6 minus 2x minus 3y dy dx. You see?
Okay.
That's a two-way you can do it, the triple or the double.
I can get the same thing.
You get the same thing. Yeah, it's the same thing because you see, because there is a 1 here.
Yeah, okay, yeah.
Yeah, you see, when you take respect to the z, you drop it down here. Then you, because of negative 2/3, you got to be patient to integrate it. We try to give you
Okay.
something nice, but you got to be patient. You know that, then you integrate and go on. Okay?
Okay, all right, thanks.
Yeah, okay. But, be patient. You may be given the, the similar one. Just get practice to be able to, to continue and take care of it.
Okay, will do. Thanks.
Okay, that's it. So I'm coming back in a minute. Okay, so we are going to look at this problem. Okay, we want to use the cylindrical coordinates to find the volume of the solid G, which is bounded above by a sphere and below by the coin. It's like it's going to be like a kind of the ice cream. It's going to be the one that we have. Okay, this is going to be the coin. This is bounded above by the sphere. It's going to be a sphere on the top, and the below by this one. So it's going to be a solid in between, and then you want to find the volume of that solid. So the volume can be done by the double integral or triple integral. For this one, we're using the triple integral. Remember, if you consider the function to be 1 in the triple, that give you the volume. So the solution is going to be, okay, so this is what you are going to have for your volume. The volume is going to be the triple integral, okay, over G, but the function that we're going to use is going to be just 1, and you know that this is going to be dV, which is going to be changing to the dx, dy, dc, and then you integrate it. So the difficulty for this one is you have to determine what is going to be the, okay, what's going to be the range of the limit of integration. And for this one, you can set it up in XY coordinate first, then change it to the cylindrical one, because they ask you to use cylindrical coordinate to do it. So we have to identify the X, Y, Z. First thing to do, you look for the Z. The number that you have for Z, if it's going to be just a fixed number, one expression for the Z, then get 0 to Z and you're done. But your Z here is, your region is like a region between two surfaces, if you like, two solids, if you like. And the top one is going to be the sphere and the below one is going to be the coin. As you did it for the ordinary one. So what you have to do is, in order to get the Z, you have to consider, okay, so you have to solve the first one for the Z to get the Z between two numbers, okay? Below, you know that it's going to be the Z. So what we do is, we're just working on the sphere part. So this is what we have for the Z. For the Z, for the coin part, this is the one, x squared plus y squared. Okay, and for the sphere, you have the x squared plus y squared plus z squared equal to the 16. So what we do is we solve this one for z, so that gives you z squared is equal to the 16 minus x squared minus y squared. Okay, and we take the positive square root here. That gives us the one on the top that we have. Is a 16 minus x squared minus y squared. So your z now is going to be, as it is given to you, they say from below is just the coin. Okay, and the top is just this hemisphere, if you like. Is a 16 minus x squared minus y squared. This is going to be the range of the z. Any question? Now to get the x and the y, you have to project this region into two-dimensional to find out what's going to be the range of these numbers. So the projection of the, you see, projection on or onto XY plane. I've given this one several times on the test. The people, the way to do it, because they know that if you want to project it, usually let z equal to the 0. They let z equal to the 0. Then they arrive at the fact that x squared plus y squared to the 16, and they take in two-dimensional, the region is going to be a circle centered at 0 with a radius of 4. Then they continue, which is wrong. Because the region is going to be, you see, because you have the intersection between these two. You have two z's over here to be able to do it. So z equal to the 0 is not going to give you the region in two-dimensional. You have to eliminate the z between these two. Eliminate the z, the leftover is going to be an equation in x and the y. So that's the difference between this type of idea that you have. So you go back to that system that you have. You have one z, it's x squared plus y squared. And you have the other one. See, this is it. You have the other one, which is going to be 16 minus x squared minus y squared. So you let these two be equal to each other to find their intersection. Their intersection is going to be, okay, a region in two-dimensional, and that would take care of the x and the y. So if you let them be equal to each other, this is what you are going to have. Now, if you square both sides, so if you square both sides, so that gives x squared plus y squared, which is equal to the 16 minus x squared minus y squared. Okay, now you move them into the one side to get the shape of this region. So that give you what? You move it to the other side, so that give you x squared plus y squared, and you get x squared plus y squared equal to 16. So the result is going to be 2x squared. You see 2x squared plus 2y squared equal to 16. So that gives x squared plus y squared equal to what? Equal to the 8. This is the shape of the region in two-dimensional. Okay? If there were not two surfaces, yes, you let z equal to the 0, you drop it down in two-dimensional. But your region is bounded by two other objects. You see the top and the bottom. So that's why you eliminate, okay, you eliminate the z, so that gives you the one. This is the projection. You see, this is the projection. This is the projection of the original one region, G, onto XY plane. Okay, and you know that this is going to be a circle. So the way you are going to do it in cylindrical coordinates, you just need it to change it to the polar coordinates. Okay, it's a circle with the center as 0 and the radius of what? Okay, so your r squared is equal to the 8. Okay, so your r is going to be 2 radical 2. So this means your r is going to be between, okay, your r is, eventually r is going to be between 0 and 2 radical 2 over 2. And you can stay with the x and the y to see it, to get there, you know, the semicircle to the top, to the bottom. You can change it to the r and quickly go to the cylindrical coordinate. So your r is going to be between 0 and 2 radical 2. Okay, this is going to be your r. Then you have to find out what is going to be the data over here, and the data is the full circle, which is going to be 0 and 2. 0 and 2 pi to get these numbers done. Any question? Now we are ready to change it into the cylindrical coordinate and take care of the problem. So the point is, when you have the intersection of two different regions, you got to be careful. The way we are going to, okay, the way you are going to find the projection into two-dimensional. It's not the case that z equal to the 0. You have two z values. You have two z values, you let them equal to each other, automatically the z will disappear, and you get an equation in two-dimensional, which is in this case going to be a circle, and then you can set up the integral in, okay, in cylindrical coordinate. So this is going to be the volume in cylindrical coordinate. Okay, so what's going to be your volume? Remember, you go with the data first, 0 to 2 pi. You go with the r first, the radius, 2 radical 2. Then you go with the z. What is the z now? We are not ready, okay? So the z is, look at the z. I forgot to check the z first. Okay, I'll put it here on the top. You see your z is between, the bottom was x squared plus y squared. and the top was 16 minus x squared plus y squared. Remember, you have to change this one into the r. X squared plus y squared is r squared, so that gives a radical r squared. Okay, less than equal to, and this is going to be 16 minus r squared. So your z is between r and radical 16 minus r squared. This is going to be the range of the, as we did it for the other ones. Okay, so now we're taking is from r to a square root of 16 minus r squared. Now the function is 1 because it's a volume problem. Its a cylindrical coordinate is going to be what? Is r dz dr d data, and easily can be integrated and get the result. Okay, so to practice, you can check the problem, the last problem on the review. I just changed this. This is 16. I think I changed it to the 4, but it's the same thing. Now we integrate it. Easy to integrate. Integrate respect to the z first. So it's going to be 0 to 2 pi, 0 to 2 pi, 0 to 2 radical 2. Integral would be r times z, but z going from r to the square root of 16 minus r squared. And when you're done, you're going to take the integral respect to the r data. You substitute, so it's going to be 0 to 2 pi. Okay, 0 to 2 radical 2. When you substitute z equal to that radical, that give you r radical 16 minus r squared, minus, you replace the z by r, so that give you r times r, and then when you're done, integrate respect to the r, then respect to the data. r would be r squared, so it's going to be 0 to 2 pi, 0 to 2 radical 2. Okay, and this is going to be r times what? R times 16 minus r squared to the half, minus r squared, and the dr d data. You have to take care of this integral minus. Okay, the second part is easy because that gives you r cubed over 3. Use substitution for this one. You need a negative half to be able to take care of it. So you better, break it in 2 parts and integrate it and continue. So it's going to be 0 to 2 pi. Okay, 0 to 2 pi because of that use substitution that I need. So what I'm going to do is, this is 0 to 2 radical 2. I need again a negative 2 here, so I rewrite this one as a negative half. Okay, this is going to be negative half. Then that give me 16 minus r squared. This is negative 2r dr. Okay, and this is going to be minus r squared dr. If you don't like it, you can bring it out and then integrate it for the u substitution. And there is a 1/2 here. So this is going to be your u. This is going to be your du. So this would be integral of u to the half du. So this is going to be 0 to 2 pi. Okay, negative 1/2. 16 minus r squared, 1/2 plus 1, 3/2 over the 3/2. And integral of r squared would be r cubed over 3. Okay, and you are going to evaluate it from 0 to 2 radical 2. When you're done, we get it to the data. Okay, you substitute, it's going to be a little bit messy because of these numbers, but it would be fine. You flip this one first. It's going to be 0 to 2 pi. And this is a negative 1/2 times it by 2/3. That's a 16 minus r squared to the 3/2 and minus r cubed over 3. and everything going from 0 to 2 radical 2 and the d data. So these two would cancel out. Is a negative 1/3, so it's going to be 0 to 2 pi. Negative 1/3 times 16 minus r squared to the 3/2 minus r cubed over 3, and this is going from 0 to 2 radical 2 d data. Okay, then you have to substitute these numbers and work on this to get the final answer patiently, okay, because of that radical. So this is it. It's going to be 0 to 2 pi, negative 1/3, 16 minus r squared. R is 2 radical 2, which is like a radical 8. So that gives you 16 minus 8 if you substitute. Okay, 2 radical 2 squared. I can write it down so that you know what's going on. It's a 2 radical 2 all squared, then the 3/2 minus 2 radical 2 to the 3rd over 3. Now when you put the 0, it's going to be minus, you get it here. Okay, it's going to be minus negative 1/3. Negative 1/3, 16 to the 3/2. Then you have the d data. Okay, when you put the 0, 16 minus r squared would just 16, and this would be 0. A little bit more simplification. This is going to be simply 16 minus 8, which is equal to the 8. So it's a 0 to 2 pi, 0 to 2 pi, negative 1/3, okay, 8 to the 3/2. We can simplify it. And this is going to be minus, if you square it, if you cube it. If you square it, that gives you 8, but you have a 2 radical 2, so that gives you 16 radical 2 over 3. That's the one, and this is going to be plus 16 to the 3/2. 16 to the 1/2 would be 4, so 4 cubed, 64. 64/3, and d data. Okay, it's going to be messy, it's unavoidable for this group of numbers. So this is going to be just a number. If you want to simplify it again, so it's 0 to 2 pi, 8 to the 3/2. Okay, so that gives you the way you can do it. 8 to the 1/2 would be 2 radical 2. Then you cube it to get these numbers. Okay. So what is the best way to simplify it? It's going to be 1/3. So you can use your calculator to get this one. Because 8 to the 8, you can cube the 8, then divide it by, then you get the square root of. It's like the square root of. Okay. You can have something like 8. This is it. Because 8 to the 3/2 is like 8 to the 1.5. So you get a 0.5 here. Okay, and this is going to be minus 16 radical 2 over 3, and the leftover 64 over 3, then the d data. Okay, you can put all of them together. Eventually, you get something like, this is 8 radical 8. It's going to be again 16 radical 2. Okay, and then you can put this together. So that gives you something like 16 radical 2 again. Let me just go to the next page to explain it. It's going to be messy, but it can be done. Radical 8 would be 2 radical 2. So that gives 16 radical 2 here and the 16 radical 2 here. So you add them together, that gives you 32 radical 2 over radical 3. So it is going to be equal to 0 to 2 pi Okay, negative 32 radical 2 over 3 plus 64 over 3 d data. So we can use your calculator if you like, but integral of d data would be 2 data 0 to 2 pi. So it's going to be negative 32 radical 2 over 3 plus 64 over 3. And this is going to be 2 data going from 0 to 2 pi. Okay, just data. So the final answer is going to be, this is 3 minus 32 radical 2 plus 64 times it by 2 pi. Okay. And you can multiply the two, or whatever you like to write the final answer. So it's going to be negative 64 radical 2 plus 128 over 3 times pi. So it's unavoidable. Whatever you arrange the number, eventually you will get to this radical format. Okay, so the important part is really how you set up that original integral. And when you do that intersection part, this is the best you can have, or this is the worst you can have when you go with a cylindrical coord. Otherwise, the problems are not difficult, and it can be somehow easily handled when you do a couple of them to get you through it. Okay, any question? So that is the cylindrical version. So if I go back, you have two in your in your review. This is the last one. Problem, I think, is number 10 or number 11. There is another one. I'm going to explain it for you, but the topics that you're going to see on the on the test, we give you one problem on, this is topic number 1, relative extremum or extrema. Okay, and this is the second derivative test, remember, from your quiz. That is a second derivative test. It's the only problem that you get from chapter 13. So that's your topic number 1. Topic number 2 is going to be evaluation of the double integral, just ordinary one. Okay, evaluate, like your quiz, a double integral, straightforward one. The range, everything would be given to you. You don't have to set it up. Again, something similar to the triple integral. A triple, got to be patient here. Integral, just ordinary one, ordinary region. Then number 4, double integral by reversing the order. Double integral by reversing the order. The order of integration, you know that you switch the order and easily can be integrated. Then the number 5 is a double integral in polar form. Double integral in a polar form. Unless you know that, x equal to the r cosine of the data, y equal to the r sine of the data. We did quite a lot, and you have some nice one in your practice one. Just read it, the similar one would be given to you. Okay, then this is going to be triple integral in cylindrical form. Cylindrical coordinates. We give it 2 here, and the other one is going to be kind of the volume. The volume would be given to you. Okay, you have a couple of the volume, but maybe the volume in cylindrical coordinate again, because you get 2 questions that you have to do the cylindrical coordinate for us. Okay, and the number 8 is going to be number 8, surface area. Okay, evaluate the surface area. Remember, you have to bring the formula AS, the surface integral. Okay, So these are going to be the topics. So you may get one more of these double integral that you have to set up the problems, okay? Because we give you, are going to have 10 questions and you answer 9. Okay, so that's going to be the volume. Again, volume. This volume can be in two-dimensional, in double or using double or triple. Double or triple integral. Triple integral. These are the topics. If you study your review really and your quiz, you should be fine to be able to do it because we give you so many examples and the test. So what else can you be given? So it's going to be 10 questions. You answered 9, 2.5 hours. Yes.
Professor, for number 3, do we need to set it up or will you give us all the values?
There are 2 cases. You
Okay.
may be given, one of them would be given straightforward, 2 and 3 straightforward. And so that setting up, maybe you're setting up for the volume, okay, or you're setting up as is. You see, this is the nature of these problems because you are going to set up one yourself. That's going to be type 1 or type 2. And it doesn't matter. It maybe comes with a double integral or triple integral. And you see, that is going to be the case. But 2 of those are going to be straightforward. So the range, everything would be nicely given to you. And just make sure you are not making any mistakes. Okay, that's it. That's a topic that we're going to have. Those 9-1. And we repeat it on the final. So we just, we shrink it for the final, but the topics are going to be, you are not going to have the first one on the final. See, this would be out. And this would be out, and we give you 10 questions on the final, and you answer 12. So we need something like 4 more questions. One of them is going to be change of variable, spherical coordinate, and a couple of questions. We're sharing this when we get to the final, but the topic is going to be the same. So we are going to learn 2 other types of integrals to be able to do it. Okay, number 9 sets volume. Finding the volume using double or triple integrals. Okay, volume using the double or triple integrals. And you have all the examples on your practice one. Okay, study your practice quiz. Okay, practice quiz, practice test. So that would be quite a lot. All the nice problems that you think about it are over there. Okay.
How much
So
time are we given for the final?
what for what?
How much time are we given on the final?
For the final 2 hours, because that's the official time of the college. Okay, the midterms I give you 2.5 hours myself. But the final is 2 hours, but the problem are shorter. So it can be done it can be done nicely 2 hours. I used to give 15 questions on the final. But because the new parts that we're going to learn, it's a kind of straightforward. And the problem that we select for the final, it's the same topics, but it's going to be short. So because we cannot give you more than 2 hours for the final, it's the official, especially because we do the problems, okay, through I cannot give you fewer questions because that would be very bad for you. Because, if you miss one of the problems, even with the 12 question is the case. But, we have done it before and the people do it so nicely. Nothing to worry about. Okay, so this is going to be the situation we're going to have. Let me just explain. There were 2 cylindrical one on this, on this review. And they are, you have question number 5. Question number 5 is much easier what we did, but we can check it quickly. So make sure you know it. Number 5, you use a cylindrical coordinate to find the volume of the solid bounded by, maybe I did this one during the lecture, but I just quickly set up the problem to show you how we're going to do it. Okay, so just read the topics. You have the review. Okay, make sure you know everything about those problems on the review, really. You have the best problem. And you can, you can have the practice, or you can watch the videos that I have, because they're all the same thing. And this is going to be the case. So this is the problem. You have the two cylindrical coordinate on this review. The problem number 10 is the last one that I gave you. Okay, this big one. That was the problem number 10. Okay, but you have a couple of them, but let me see. You have number 7. Okay, number 7 is easy. How much time do I have? I don't have much time. Number 7, these functions are easy. For example, you want to use cylindrical coordinate, for example, to find this one. By the things that we discuss, you should be able to do these problems quickly, really. Okay, and the one that you have is going to be just straightforward. It's 1 over x squared plus y squared, x squared plus y squared, and the dz, dy, dx. They ask cylindrical coordinate to do it. Now you know that. Quickly, remember, introduce the region. Change it to the polar coordinate in 2-dimensional and go for it. So solution, zyx. So x is the last one. -2, 2. In the middle, y. Oh, that's interesting. Okay, y. In the middle. Outside, z. Between 0 and 1 over x squared plus y squared. You focus on this one. Okay. You see, you don't have a negative and positive. So this means this is the semicircle. You see, it's a semicircle. That is the upper part. You see, semicircle squared. So that gives you x squared plus y squared equal to 4. So you realize that you have a circle. Okay. So far, you see this is 0. The radius of 2, 1, 2, 1, 2. You see, you don't have a positive, negative. You have only positive. So you are going to have only the upper part. Upper part so far, -2 and 2. Then you check the x. X is between -2 and 2. So you have only the upper part. You see, that's the one. Any question? So that's, the one that we did, it was a positive, negative. So we just, we picked a full circle. But in this case, you have 0 here. Okay, it's just the upper part, and you have a negative. Sometimes you have the x between 0 and 2. If it was 0 and 2, then even you have a first quarter, like the problem that we did before. So now you are going to find your r. The radius is 2. So r is between 0 and 2. Then you go for the data, it's just the upper part. So the data is going to be 0 and pi. Any question? So that's a 2-dimensional one. Z must be what? Must be a function of r and data. Must be a fixed number. Or if it's going to be anything else, you substitute for the x squared plus y squared. You know that x squared plus y squared would be r squared. So your z would be, okay, this is going to be your z. You just substitute right away. Because the x squared plus y squared is r squared, you change the z into the function of r and data. So your z is between 0. Okay, z is going to be between 0 and 1 minus r squared. That's it. As long as z is a function of r and data, you are safe. Now it's ready to be done. Okay. So let's see. This is it. Go back and start integrating. By the formula that we have, I equal to, we integrate respect to the data. The data is 0 to pi, 0 to pi. We integrate respect to r, 0 to 2. Then we start integrating respect to the z first. Z is between 0 and 1 over r squared. Function. The function is radical x squared plus y squared. You have to change it. You know that x squared plus y squared is r squared. So it's going to be radical r squared. Then remember r dz dr d data. For the cylindrical coordinate, there is a r here, dz dr d data. Okay, radical r squared with just r, so it's going to be equal to, I rewrite it, it's 0 to pi, 0 to 2, 0 to 1 over r squared. So this is r times r, you see r, and this is it, r, if you like, and that's a dz dr d data. So r would be r squared, 0 to pi, 0 to 2, 0 to 1 over r squared. So r squared, dz dr d data. Okay, now integrate respect to the z. So that gives 0 to pi, 0 to 2. Okay, integral of r squared is going to be r squared z. Z between 0 and 1 over r squared. And when you're done, dr d data. You substitute, it's going to be 0 to pi, 0 to 2, r squared z. So that gives you r squared z, z1 over r squared. And when z is equal to the 0, that would be 0. Then the dr d data. Okay, if you multiply that, give you 1. So 0 to pi, 0 to 2, simply dr d data. Okay, dr d data, which is going to be 0 to pi. The integral would be just r going from 0 to 2, then the d data. So it's going to be 0 to pi, just 2. D data is going to be 2 data from 0 to pi, 2 pi, the final answer. Okay, so this is the way you are going to do it. That's it. Any question? So read the practice one. If you have any question, you can email me. Okay, I'll be in this conference, but if you email me, I can get back to you during the break that we have. Okay, so review this. If you have any question, and then as we talk about it on Thursday, depends whether the college would get back to the normal or not. But okay, Professor Scott, if it's going to be online, he will just let you know. Okay, it's using the same link. Otherwise, the class as usual. And then you can start taking the test on Thursday. Okay, the question are already ready for you. That's it. Good luck. I'll post this. If you want, somebody said I made this lecture notes, I will post it later tonight for you. Okay, and again, study your practice quiz. I look at your quiz and I check it and I grade it before just before the end of the week. Then if I need, I just post the solution for that as well. Okay, read your quiz again. Okay, read your quiz again, put them all together, and you should be fine really to get these numbers. Again, some of you, you can drop Lowe's test, Lowe's quiz, but you better take this test even if you want to drop it. Okay, take this test to see how you're handling the problems, because you have to handle it on the final. So you better practice even if you don't want to, okay, seriously take it. Okay, because it's a couple of weeks, that will be the final. Okay, have a good one and let me know if you need anything. Okay, take care. Bye-bye.
Thank you, Professor. Have a good one.
Thank you.
Bye-bye. Thank you. Bye.